electric field at the center of the semicircle. A thin plastic rod is bent so that it has a shape of semicircle of radius r. So the radius of the r is given, which is 7 meters. Then amount of charge Q, total Q charge is given 34 microcoulomb. As you can see, it's positive charge is distributed along the rod. What is the magnitude of the electric field at the center of the circle point P? So we have to find total electric field at point P. Okay, so what we have to do? Since it's very thin rod, so what I'm going to do is basically I'm going to make it kind of little bit kind of thin rod. Okay, now then you have to divide it into small piece. Okay, let's say that you're going to divide this part is very small piece. It's a bit tough. Anyway, small piece, and at the same distance try to divide small pieces, and that small piece is equal to the small charge dq. Okay, what about the length of this dq? The length of this dq will be very small, which is dl. Now don't forget that this whole length of the semicircle is L. Okay, so if it's L, then the length of this semicircle length is equal to the pi r. Okay, and this dq will emit electric field, so it will create electric field which is very small, so I call this one as a de. Okay, what else? Then this will make very small angle, correct? So this will make very small angle, so this angle will be d theta. Okay, so this is r. Now since this de directed at a certain angle, so de can be resolved into two components. One will be de y, and another one will be de x. Okay, now if you try to do the same thing for the at the same distance at this point, this dq1, then you can see that it will make electric field same this de1, and this de1 will have two components, so de 1y, and this one will make de x1. Okay, and as you can see here, this x components will cancel each other. Okay, why? Because they have same magnitude but opposite in direction. So the only thing will add up will be only y components of the electric field. Okay, so that means what we have to do, we have to find total electric field, which is in y component. Ey will be equal to the integral of the dEy. Okay, now dEy is equal to what? dEy is equal to the dE, which is this component, multiplied to the theta. Okay, so if you say this is any theta, that will give you dE sine theta. Okay, what about the limits now? The limits, if you take this one as a 0, okay, this will be the pi, and if you go here up to here, it will make 2 pi, correct? So that means you can say from pi to 2 pi. Okay, now what about dE? So dE is equal to what? dE is equal to the k dq divided by the r squared. Okay, then what about dq? dq is equal to the lambda multiplied to the dl. Okay, or we know that lambda is equal to total Q divided by the L, or dq divided by the dl. Okay. Then what else? So what about the dl then? dl, which is very small, this one, dl is equal to the r d theta. Okay, so let's plug everything to this formula, where we have dE is equal k, dq is equal to the lambda, so dl is equal to the lambda r d theta, correct? So that means k lambda r d theta divided by the r squared, so we'll cancel out, so it will end up with k lambda d theta divided by the r. Okay, so then finally you come here and you put there, so that means integral of the k lambda divided by the r sine theta d theta. So that means you have to integrate sine theta. Okay, so you might be asking, so what is our lambda then? The lambda is total charge divided by the L. Now, what is the length in our case? In our case, the length, so the lambda is equal total charge divided by the L will be pi r. So that's it. If you plug and integrate it, you should get the answer.